today we will be starting a new session on the course Line Commutated and PWM Rectifiers.
Having understood this transformer properties, right, now let us introduce the actual converter to you. Okay, we will insert this transformer into the flyback converter. You can see here there is a transformer here, and of course now we have replaced that S1 with a MOSFET here, S2 with a diode here. This was the S2 earlier. Okay, we have a source, right, and we also have a load here, and we have the capacitor here. Okay, this is a 1:n transformer. Okay, now this is the structure of a flyback converter. It is actually one of the simplest isolated DC-DC converter. One of the most important advantage of the flyback converter, as you can understand here, is that there is no separate inductor. The transformer is behaving as an inductor here in this configuration. And so this converter is quite popular because it has no separate space and volume and size, no separate space, volume, size needs to be allocated for the inductor for this isolated DC-DC converter. Other types of converter like a forward converter will have a separate inductor along with the isolation. So that way flyback converter in that respect is more compact in size. Okay, but at the other side there is also one more, the capacitor size will go up. That's we'll talk about it later. Okay, now it is based on the buck boost converter principle, which we will derive very soon how this will work. The other thing is you have to note the polarity, very important. You see here, we have put a dot here and we have put a dot here. Okay, this is very important. Okay, we have put the windings in this way. We have made the windings. And one of the things, as we have already told, that one of the important difference with this transformer and the conventional 50 hertz sinusoidal AC grid transformer, the important difference is current is not flowing simultaneously in both the windings. Okay, so sometimes current is flowing in this winding and sometimes it is flowing in the secondary winding. Okay, not simultaneously, not at the same time. Okay, okay. So what is the overall philosophy? The overall philosophy is that initially MOSFET S1 will conduct. So this is, you can see here, the MOSFET S1 is conducting. Energy will get stored from the DC source into LM. Okay, so this way current will flow and energy will go stored in the LM. Note that current is not flowing in the secondary. Okay, no current is flowing in the secondary, right? So therefore, in this winding, in the primary winding, not exactly primary winding, in this part of the circuit, okay, where I have shown this part of the circuit, no current can flow. Okay, current is flowing in the primary winding, remember, but that current is flowing through this inductor here, and that inductor, that means that the primary winding current is entirely utilized to store energy in the core of the transformer. But in the circuit, which I have shown, there is no current flowing here and there is no current flowing here. Okay. Now, yeah. So another thing is D1 is not conducting because it is reverse bias due to the dot polarity. How will you understand this? When S1 is conducting, just hold on. We'll take the rubber and we'll delete this one. When S1 is conducting, then this voltage here, this is a dot and this is the dot. Okay, so we are following the dot principle. So therefore, V in by 1 equal to this voltage is, so V0 by N, right? So therefore, this voltage here, which is coming, is with this is plus, because we have applied a plus voltage. We have the V in is plus here. Okay, so we have applied a plus voltage here. So which means this point's voltage is also plus. What is the magnitude? The magnitude is V0 equal to N times V in. This magnitude of voltage is there, right? So this voltage comes here along with this one. So on the diode, okay, so here is your diode. The diode is here. Okay, on this diode, this point is minus, this is connected here. But you see the total voltage that comes across the diode is reverse biased, because now if you apply KVL, the total voltage that is coming across the diode is V0 plus in V in. Okay, this is the total voltage that is coming across the diode, which is basically reverse biasing the diode. Okay, you can see here, and that's why the diode will not conduct. So when the switch S1 turns on, the diode is reverse biased by this voltage and it will not conduct, right? Uh, and since the diode is not conducting, therefore the output capacitor, you can see here, this output capacitor is going to supply the entire load. Okay, yeah, basically, uh, therefore, what does this mean? That the capacitor, when the switch is during the turn on time of the converter, the capacitor is fully supplying the load, which means that if you want the capacitor voltage not to go down substantially, you need a very big capacitor, because you have to supply the entire load during the whole of on time from the capacitor into the load. Okay, so you need a bigger capacitor as compared to some other converters where you have sometimes like a buck converter or something, we have inductors in addition to capacitors which supply energy to the load. Okay, but in this case, the capacitor has the responsibility to supply the entire demand of the load during this time. So therefore, this is the disadvantage. Okay, so you can understand here also in a more philosophical sense, you cannot have the perfect converter. You get something, you lose something. Okay, so here it is like this. Now, when MOSFET is S1 turns off, okay, suppose this condition, suppose we have withdrawn the gate pulses to S1, then S1 will turn off. And then immediately you can understand that this current, okay, the ILM, this current was already flowing. It needs a path, okay, to complete. It was flowing. It will go like this, okay. It will flow like this, right? So basically, LM is the code, the corresponding to the energy or the flux in the core. It will now die down, okay, because you have opened the S1 switch and the V in source has been isolated. So now this code will die down, the energy in the code will die down, but you note that the current through the inductor is now going out of the dot terminal. Okay, so which means current will enter through the dot terminal on the secondary side. Okay, remember the dot principle. Current entering into one dot terminal will cause the current to go out of the dot terminal in the second one. So you can see here that this current is entering the dot terminal. Obviously, the diode D1 will now get forward biased. Okay, and therefore it will now feed the load, and as well as it will charge up the capacitor. The capacitors have already lost energy. Now we are replenishing the capacitor. Output capacitor is replenished. Okay, and the stored energy which was there in the inductor or in the core of the transformer, that energy is getting transferred to the load. Okay, of course there is also this inductor voltage and current scaling is there, because there is a 1:n transformer. A scaling will be happening And that scaling we will see from the equations once we see. But this is the overall idea of the operation of the converter. Okay. So now we can actually write down these equations. Okay. What happens when S1 conducts, what happens when D1 conducts, like that. Okay, so in the subinterval 1, so we have this S1 conducting and D1 conducting, and we have plotted some of the important voltage and currents in the circuit. Okay, now during subinterval 1, okay, S1 is conducting, and then the following relationship holds. Okay, so voltage across, as I have told, voltage across the diode is in V in plus V0. Okay, I think we had written it. Yes, in here it was shown here, V0 plus in V in. And so here the voltage across the is in V in plus V0. And so it will be reverse biased, and this we have the circuit now. So in this circuit, what we observe is VLM, okay, VLM is equal to V in is equal to L times di by dt, coming from the basic equation. So which means this ILM, so this is the VLM voltage. We have put a V in here. Okay, you can understand V in here. And therefore, this ILM current will increase. Okay, slightly it will increase. Okay, depending on the value of LM, of course. And so we will have a ripple on this current, okay, which is given by delta ILM. Okay, during this time, right, the V2 voltage is of course the secondary voltage, which is N times V in, with the plus here, the plus here, and the plus here. Okay, right, V2 equal to NV in. And how much is IC? IC equal to minus V0 by R, right? And minus V0. So IC here, because the current, the capacitor is now supplying to the load, okay? And it is minus V0 by R, right? And yeah, and I in is equal to ILM. So this input current I in, you can see it is same as ILM here. This and this are same, right? I in. This is the condition. Now, if the switch is on for D times TS period, which we have seen here, if the switch is on for this much time period, then we can find out how much is the ripple, how much is the increase in the inductor current. So delta ILM is V in into DTS divided by LM. Okay, V in. So coming from this equation, okay, V in into dt becomes capital DTS, and DILM becomes delta ILM and divided by LM. Okay, so this is the equation during this time. Now, what will happen during subinterval 2 when D1 is conducting? Then the following relationship holds. Okay, then in that case, VLM here is minus V0 by N. Why is it minus? Because whenever the diode is conducting here, so as I told you, this voltage is plus and this voltage is plus. So now you can see, because we have a voltage V0, okay, so what will come back on the primary side here is this voltage V0, because it is coming here, and divided by the turns ratio, right? Because during this time, V1 by 1 equal to minus V0 by N, right? So therefore, VLM is equal to minus V0 divided by N. We have a 1 is to N, we have a 1 is to N transformer, right? So this VLM is coming here. You can see here V minus, when D1 is conducting, you have minus V0 by N. Okay. Okay. This is LM into D and dt. IC equal to, what is IC? Now, IC will be equal to ILM by N minus V0 by R. Okay. How does it come? Because there will be some current which is flowing from this side, which this current will be ILM by N, because ILM is flowing here, which is also flowing through this winding. And so ILM by N is the reflected secondary current. And out of that, V0 by R will flow into this load, and the rest of the current IC, which is this current here, will be this much. Okay, this comes from KCL. Okay, and I in is equal to 0. This current I in is equal to 0 because now the switch has isolated completely the input voltage source from the transformer. Okay. So the voltage across MOSFET is V in plus V0 by N. How does it come? Because if you look into this voltage here, okay, let me. So what is the voltage that comes across the MOSFET here? Okay, of course, this will be uh, V in voltage is already there, plus V0 by N, which is V0 by N is coming from here. Okay, this voltage is V0 by N. So V0 by N plus V in. This is the blocking voltage required for the MOSFET. Okay, this much of voltage will come. Now, if the diode is on for D dash TDS, where D dash is equal to 1 minus D. Okay, if it is on for the D dash time period, then we will say delta ILMT, this fall of the current. Okay, again, fall of the current is this much. Okay, right. So this dt now gets replaced by 1 minus d times ts. Okay, and so we can write down this equation from here. Right. Okay, so we have got this one. Now we are assuming the converter is working in CCM, continuous conduction mode. We will later see in the next sometime later, when we are talking with AC/DC flyback converter, we will talk more in details about the discontinuous conduction mode. Okay, because AC/DC flyback converters usually work with DCM mode. But here we assume that the converter is operating in CCM. So what is the CCM means? CCM means that, if you do not know it, CCM means that this current through the inductor, okay, does not touch zero at the end of the cycle. So here you can see there is a finite positive value to this inductor current, and that is why it is called CCM. In a DC or in the critical conduction mode, the current will become something like this. It starts from 0, ends in 0. Okay, it starts from 0, ends in 0. Again starts from 0, ends in 0. This is CRCM, critical conduction mode. Okay, and in DCM, what happens is the current starts from 0 but ends in 0 before the DTS time period is over. Okay, so starts from 0, goes up, comes back, and remains 0 for some time. Then again starts and then again goes to 0 and remains 0 for some time. This is the DCM operation, discontinuous conduction mode. Okay, we will talk about it later. Okay, not now. So let us, for the time being, assume that, let us not talk about it. Let us get these things all removed. Okay, sorry. Yeah, we are operating in the CCM mode. Okay. Yeah. So we have designed LM and C, okay, such that now in the CCM we are saying that LM and C are designed in such a way that the inductor current ripple and capacitor voltage is very small. Okay, that is delta ILM is much less than ILM, which means this delta ILM, this ripple is basically much smaller than the average component. Okay, much less than this. And similarly, delta V0 is much less than V0. So this delta V0 is the ripple on the capacitor voltage, which is much less than V0. Okay, so we are assuming this. This second assumption is more or less always maintained. But the first assumption under DCM or under critical conduction mode, this is not maintained. Okay, so it is very difficult. I mean, we will have to change certain things there. But this condition, delta V0 much less than V0, is always maintained in a flyback converter. Now, suppose we have this CCM operation and we have these conditions satisfied or valid, which means delta V0 is much less than V0 here, and delta ILM is much less than ILM. Okay. So then we can say this ILM is almost equal to capital ILM and V0 is almost equal to capital I. Now this will be used for deriving the volt second balance, from where we will get the input output voltage relationship, which is shown in the next slide. So here, if you apply the volt second balance, okay, volt second balance means what? The voltage across the inductor in the on period and the voltage across the inductor during off period, the sum of them should be equal to 0. Okay, so the voltage applied in the inductor will be V in into ds. So you can see this from the curve. V in is the voltage applied for dts time period, and minus V0 by n is applied for d dash t. Here you see what we have done. That is where this small ripple approximation was useful, that I have changed this to capital V0. Okay, you see here, this is the reason I had done, or I had shown the previous slide. Okay, so minus capital V0 by n into d dash into ts, that is equal to 0. And so capital V0, this is the steady average output voltage, is n times d by d dash into v in. So I can also write it like n times d by 1 minus d times v in. Okay, so we can see that the flyback converter is an isolated buck boost converter. Okay, that is what we understand from this one. Okay, but so this is the buck boost converter relationship. But in addition, we have this factor which is coming from the transformer turns ratio. Okay, this is what is important here. We can also do the charge balance and we can get all the currents which are flowing. What does this charge balance means? That the net charge in the capacitor should be equal to 0. Okay, because otherwise the capacitor will go on charging, its voltage will go on increasing or will go on decreasing to 0, right? So therefore, if I apply the principle of charge balance, okay, so this is the current which is flowing to the capacitor. Again, I have used minus capital V0. I'm assuming that the output voltage is relatively constant using the small ripple approximation. So this is the charge, okay, minus V0 by R into the dts time. This is the charge flowing out of the capacitor. What is coming inside the capacitor is this much. Okay, ILM by n minus V0 by R into d dash into ts. This is the current which is flowing inside the capacitor. You can see here. This is the current flowing in the capacitor for a d dash time period. And therefore, the average from these two equations, the average value of the currents can be obtained. Okay, average value of the inductor current in terms of the output current. Okay, this output current is obtained, right? Um, right. Um, so this we can get it. Uh, so we can write this equation in different way. I mean, in terms of the output current, I'm now I can write it in this different format. Output current is now expressed as a factor of ILM. Okay, you can write it in this way also. Okay, now from the waveform, okay, from the waveform, you can see that the average value of the input current, see, input current is flowing only during this time, right? It is like this, okay? The input current, if I assume that the ILM is almost constant, right? So what is the average value of the input current? The average value of the input current will be this value here, right? This is the average value of the inductor input current. And what will be its value? Its value will be D times ILM, because it is for dt time period. So therefore, I in is D times ILM, which you can also write it in this format. Okay. So from the previous equation, from this equation, we got I0 or I output, and here we got I input, I in, IO and I in. And so we can say that I in by I0, IO is in D by D dash, which will come out to be, if you do the little bit manipulation, it will come out to be VO by V in, which means the power balance is maintained as we had earlier expected. Okay. Yeah. So now we can also find out what is the uh, output voltage ripple. How much is the output voltage ripple? So this is like delta V0 by V0. Okay. How do you get that one? What is delta V0? Delta V0 is the charge. Delta V0 is the ripple voltage which is flowing because which is happening because some charge is flowing out of the capacitor, right? And we know that Q equal to C times V. So here delta Q is will be equal to C times delta V0, right? So therefore, how much is this Q? The Q flowing is I0. Okay, out of the capacitor, you can see here, this is the I0 current which is flowing, IO current which is flowing for a time period of dts. So therefore, this is the charge which is flowing, and divided by C, Q by C is, this is a delta Q by C, which is equal to delta V0. And so if you substitute these values, you will get this equation. Okay. So delta V0 by V0 is D times RCFS, through which it is possible to design the value of C. If you suppose say that delta V0 by V0 is 0.01, I can then find out what is the value of C. Okay. So this equation will be used to design the value of C. Now this is important to keep in mind that the capacitor will carry the full load current when the diode is off. And this is something which causes this flyback converter. So the output capacitor is somewhat bigger as compared to some other isolated DC-DC converters like a forward converter. Okay. So this is the difference. It has to supply to the load. Okay. One of the things, you can see the flyback converter has an advantage because now we do not have the inductor. But you see, there are certain points to note. One of the things is the voltage across the MOSFET when it is off. We had seen earlier, it is V in plus V0, V out, V0 by in. So this is the voltage that the MOSFET has to block. Okay. Actually, so this means it is a combination of both the input and the output voltage. Okay. Uh, so this is something also true for the voltage across the diode. So when the diode is off, this voltage, when the diode was off, okay, the voltage across the diode was coming out to be V naught plus in Vn. So in both the equations, you can see that the voltage across the device, which means the blocking voltage across the device, is the sum of a certain sum of the is a combination of both input and output voltages with this turns ratio n. Okay. And therefore, in this case, in this flyback converter, the voltage across the devices is comparatively high. Okay. It is not simply as the input voltage or simply as the output voltage. It is a combination. So So I can show you some example at the bottom. Okay, here we will give you an example. The other thing that is important here is that comes from the normal practical application, and that is this the voltage spike across the MOSFET. Okay, voltage spike across the MOSFET is something which is a very practical issue which is faced by the flyback converter. So suppose if you see here, this is, I am representing the MOSFET by this switch. If you when the voltage across, when the switch is on, the voltage across the switch is 0. But when the switch is turning off, you expect the voltage to be like this. Okay, right? But it is actually not like this. The voltage across the MOSFET, when it is turning on, when it is turning off, okay, this is the voltage across the MOSFET with time, and it will be something like this. Okay, there is a spike. Okay, this spike. Okay, this spike is something which is expected because remember, earlier we had all assumed that this transformer was ideal and everything was ideal. But in real life, there is a leakage here. Okay, and there is a leakage here. Okay, all these windings, wires, everything have a leakage, right? And you are basically breaking the current in the primary winding. Remember, when we had remembered this example, right? You are breaking the primary current. You are turning on the switch, turning off the switch S1. Okay, you're breaking the primary current. So, which means all these inductors and everything in this circuit will have an LDI by dt. Okay, you are making the current fall from a finite value to 0 in a very short time. That LDI/dt will give a voltage kick, okay, and will appear across the MOSFET. This is something which must be taken care of during the design. So we have to basically put some additional buffering or additional uh, allowance in the voltage rating of the MOSFET. So here, suppose we are making a flyback converter for converting 60 volt to 5 volt, so step down. Okay, then if it is 60 to 5, then we can take about 1:10 transformation ratio, right? And then the final tuning will be done by the duty ratio. And so the voltage across the MOSFET will be how much? As we had told, the voltage across the MOSFET is, when it is turning off, is V in plus V0 by N. So therefore, this is the V in 60 volt here, and V0 is 5 volt and N is 0.1. Okay, so the voltage across the MOSFET is coming up to be 110 volt. Now, we this spike, again, this spike can be easily 30%, if not more. Okay, it can be even more than 30%. So this spike can be like 30%, 40%, something like this. So here, if I assume that this spike is 30%, so 30% of 110 is 143 volt. And therefore, we are taking a 200 volt MOSFET. Okay, this much of margin, okay, is we have to keep. Okay, like, because in real life, predicting this spike voltage is very difficult. Okay, you do not know how the windings will be, what will be the trace, PCB trace inductance, what will be the wire inductance, how much is the length of that wire. It is very difficult to predict everything beforehand. So like this, for 110 volt requirement of this MOSFET, we can take a 200 volt MOSFET or something like that, similar to this thing. Okay, we have to take this margin from the operational viewpoint. Okay, now let us take an example. We will quickly take a few examples, two examples we have. Uh, the first one is like, is simple. V in is 24 volt, V naught is 5 volt. So we are basically converting 24 volt to 5 volt isolated power supply. And we have N1 to N2 as 3, Lm as 500 microhenry, R equal to 5 ohm, C equal to 200 microfarad, and F equal to 40 kilohertz. What we are asking is find the duty ratio, maximum and minimum values of ILM, and output voltage ripple delta V0. Okay. So we have seen already V0, V output is equal to N times D by D dash into V in, and V in is equal to 24, V naught is 5, and N equal to 1/3. Hence, D is equal to 0.385. Straightforward, just by putting into the equations. Okay. And so these are practical values. The reason for giving these examples is to acquaint you with practical values. Okay. Now, average value of the inductor current, ILM, how much is the average value? So here we are taking this average value of the inductor current through the output current expression. Okay. We know what is V0 and what is R. So therefore, I0 we know already is 5 volt divided by 5 ohm. It is 1 ampere. And what is N? N equal to 1/3, and D dash is equal to 0.615. D dash is equal to 1 minus D. And so therefore the inductor value, average value of the inductor current is 542 milliampere. Okay. Now, maximum and minimum values of the inductor current can be obtained by this expression, ILM plus minus delta ILM by 2, right? And so therefore here delta ILM is equal to V in into DTS by LM, right? Because this we have seen when the switch is on, V in voltage is getting applied for DTS time period. So delta ILM will be 462 milliampere. Okay. So therefore ILM max will be this ILM plus delta ILM by 2. Okay. And so the current is 773 and 311 milliampere, right? And what is delta V0 by V0? Delta V0 by V0 is D times D divided by RCFS, which will be equal to 0.96. How do you get this? Delta V0 is mm, uh, delta V0 by this equation we had derived previously, D by RCFS, and we have got all the values here, and so the ripple is less than 1%. Okay, so this is something which we can do quickly. Now, one more thing that I would like to point out here is the CCM operation and the critical conduction mode. So the maximum and minimum values of the magnetizing current is, you can see this is like this. Okay, so it is like this. Okay, this is the inductor current. Okay, so this is the average value. Okay, ILN. And then you have the ripple, this ripple. Okay, delta ILN. Right. Now, for the CCM operation, we must have this current not touching 0, right? This value should not touch 0. Okay, it should not touch 0. At the boundary, as I told you, at the boundary, the current will be something like this. Okay, okay, but at CCM, this should not touch to 0, right? So, which means that this ILM, the average value here must be more than half of this ripple. Okay, half of this delta ILM, that ILM value should be more than that. Only then CCM will be ensured. It will be over the 0. Okay, right? So if I remove this part and redraw the red one. Okay, so this is the current and the delta ILM. So ILM, okay, the average value should be more than half of this and only then it will not touch, this part will not touch the lower 0. Okay, right? So therefore this gives a condition, or this gives a boundary condition for us to know where is CCM there and where does it uh, uh, end. Okay, so if you put these values here, in V0 are this and this one, then we get a condition of this one. Okay, so if LM is more than this value, then the CCM will happen. Okay, and if LM is less than this value, this is called the L critical. L critical is this value. If LM is less than L critical, then the inductor current reaches to 0 before the starting of the new cycle. Okay, here remember that this condition is not so important, right, in this, in our discussion today, but it will become very important when we talk about the AC-DC flyback converter. Okay, so keep this in mind. We are not yeah, we will be using this after a certain period of time later. That if what happens, note that this R value may be changing. Okay, because the load may be changing, so therefore the equivalent R of the load, that thing is changing. So R can go up and down, but we have to ensure that LM is more than this value. Okay, so yeah, this is an example. Suppose a flyback converter with an input and output voltage of 15 volt and 48 volt. Okay, step up. The load current is 1 ampere. Transformer turn switch is 1:4. The switching frequency is 150 kilohertz. Okay, find the value of LM that will cause the converter to operate at the boundary of CCM and DCM. Okay, so we have seen this one, LM, as this equation here, where what is R here? R is 48 because 48 volt divided by 1 ampere is 48. D equal to 0.444. How do you get this? Because we have 15 volt, we have 48 volt, and we have N. Okay, so we can get this value. Okay, V0 by N equal to N times D by 1 minus D. Right? So that equation will give us this value, N equal to 4 and Fs equal to 150 kilohertz. And so by putting into this value, direct substitution, Lm comes out to be close to 3 microhenry. Right? Now, what are the maximum and minimum values of this current, the transformer magnetizing current? As we have seen, maximum and minimum values of magnetizing current are this thing, right? Now, what is ILM? What is the average value of the inductor current? You can find out by using the formula before, N I0 by D dash, which will be N is 4 and I0 is, yeah, you can just, I0 is 1 ampere and D dash is 0.555, which will give you 7.2 ampere. Now, remember this converter is working, okay, at the boundary of CCM and DCM. So what does this mean? It means that the converter is working like this. Okay, so which means this average value here, this is the average value ILM. This average value is exactly half the peak value, right? Because this is a triangular waveform and the average value will be half of the peak value, right? So therefore, if the average value is 7.2, the minimum value will be, of course, 0 ampere because it is at the boundary. So the current is going to 0. But the maximum value will be double than this. Okay, so it is just double than this. It will be 14.4 ampere. Okay, but we can also verify it from the other equation of delta ILM, which will come out to be again like this. Okay, we can do it also this way. Okay, so then you can find out what are the maximum and minimum values of the inductor current through this. Okay, now we are coming towards the end of our lecture. First of all, we will talk briefly about the advantages and disadvantages of the flyback converter before we conclude. Now, flyback converter is a very popular converter and has a lot of applications for up to like 100 to 150 watt power rating. Okay, it's very useful in consumer electronics and also in LED driver. Okay, LED driver for AC-DC flyback converter. And output voltage can be less than 10 volt to hundreds of volt. One must be careful that the input current should not be excessively high. Okay, flyback converters have the tendency to saturate, okay, very quickly. This is because we are storing the energy in the transformer body or in the transformer core. So there is not, so unlike normal transformer, there is no flux cancellation or there is no MMF balancing, right? So therefore, the flyback transformers are prone to getting saturated if we are not taking additional care. It can easily saturate it because the secondary MMF is not cancelling the primary MMF, right? So therefore, you must be careful. It is also very suitable for multiple output power supply, right? So from this 100 volt input, for example, you can get 5 volt, 3.3 volt, and 15 volt outputs, right? You can get it. Okay, so this is very useful in many PCB power supplies. We see that flyback transformers, flyback converters are frequently used. Okay, what is the advantage is that if you want to have an additional output, you need an additional winding in the transformer, one capacitor and one diode. If you see the secondaries, it has only one additional winding, capacitor and the diode. There is no additional inductor. That makes your life a little bit simpler when you want to have multiple output power supply. Okay, so one transformer and no additional separate inductor. So this is the advantage. No additional separate inductor in flyback. So many people prefer this design. But there are some disadvantages. Of course, as I told you one thing, high voltage on the devices. We saw that the MOSFET and the diode voltages have a combination of both input and output voltages. So that along with the leakage inductance, the voltage spikes due to the leakage inductance, that causes a high voltage on these devices. So that is one drawback of the flyback converter. And another concern of the flyback transformer is the saturation, which I just now explained, right? Because the primary MMF is not cancelled by secondary, hence the core gets easily saturated. Okay. Now, what is the solution for this? The solution is to use gapped core or use powdered cores. Okay. What happens when you use a gapped core is that you actually you change your curve. So the slope becomes like this. If it is a high LM, the slope, because the LM is basically the slope of this BH curve. Okay. When you have a gapped code, okay, or a code with air gap, then you basically, when you introduce an air gap, you change the slope of the BH curve, right? And it becomes like this. So it becomes like this curve, like good. The slope becomes like this, right? So therefore, what happens is that if you use such a curve, what happens, you see here that in spite of increasing the H, right? In spite of increasing the H, your B is not increasing. Your B is not increasing. Okay. So you will not saturate, right? So even if you increase H, B is not increasing. And so therefore, you basically do not saturate the core. Okay. Because your core will saturate only at this value. So when you introduce an air gap, you are limited to this value of B and you will not saturate the core. Okay. In spite of the fact you are increasing quite a substantial value of H, because H is dependent on the primary current. You're going to store energy, H will increase, but B will not increase so much. Okay. And in the other case, which we were showing, in this case, if you increase this H by this much, your B will go up like this here. Okay. If you increase it, H will go up to this point. Okay. So which is going to create a problem in the saturation of the ferrite core. Okay. There is a chance because B will rapidly increase. So this is the thing that we do. We use powdered core or core with air gap, so as to prevent the saturation of the core, understanding that we have to store some energy and we have to increase the value of current. So that means we are going to increase the value of the magnetic field intensity H inside the core, but it will not saturate, should not saturate the core. Okay, because otherwise the value of L will fall, and we don't want the value of L to fall. Okay, and the last point here is only one quadrant of the BH curve is used. You can understand here that the inductor current is never negative. Okay, it is only positive in one direction, right? So which means we are basically using only this area of the BH curve. Okay, we do not go to the minus, so we are not going the other way. So this is unlike with some other converters, right? So we are not going to go into the negative side of H, and so part of the code is utilized. We are not utilizing the full first and third quadrant like that. Okay. Okay, so with this, we basically come to the conclusion of this lecture. And what we have learned here is the first part of the flyback converter, AC-DC flyback converter, in which we had discussed in details about the operation of a DC-DC flyback converter. Because if you understand the DC-DC flyback converter, then only you will understand the AC-DC, and it will become much easier. In the next lecture, we will actually go through the AC-DC flyback converter in a much quicker fashion, because all the theory, background theory, has been now analyzed in details. And we had covered, or we have understood how the transformer operates in the flyback converter. And then we have also understood how the switches are operated and how the input-output relationships are present in this kind of a converter. And in the next class, we will talk about the AC-DC flyback converter. Thank you.